divide this entire equation by Cj, because Cj is not 0. Okay? So, and this way we can express Vj as minus C1 Cj, which is a number, V1 minus C2 over Cj, and etc. So up until minus Cn over Cj to the n.
Sorry, just to clarify, this is still for part A.
So so the first part says complete the following sentence: a set of vectors is defined to be linearly dependent if. And then so one way you can say is if we make a linear combination of these vectors that is 0, then not all of the CI's are necessarily 0. We have sort of non-zero CI's which will solve them. And another equivalent definition would be to say if there exists, if one of the vectors is linearly depends on others. So if one of the vectors is a linear combination of others.
Oh, got it.
Okay? And I'm just saying that these two are equivalent. And how do you see that? Well, you take this expression, and from this you can express one vector is a combination of others.
Okay,
So if you assume that Cj is 0, would you not be able to do
Sorry, I promised that I would record this.
Oh, really?
Yeah.
Oh my God.
So, yeah. There you go. Off the camera.
Okay. So for this part in C, suppose the set of vectors UVW in R7 is linearly independent. So these are linearly independent. Is the set UV necessarily linearly independent as well? Explain why or give a counterexample illustrating why not. So what do you think?
Yes.
Yeah, so how would we prove this?
Well, if you know that UV and W are linearly independent, and those are three vectors.
Yeah, it's kind of,
Oh.
yeah. So
You could make the C value that goes with W be 0.
okay, so I think sort of the best way to prove this is by contradiction. Namely, if U and V, so this statement is equivalent, is the same as saying if U, V are dependent, then these three will be dependent, right? So U, V, W in the linearly independent. So from here, so the statement is if U, V, W are linearly independent, then U, V are linearly independent. So this statement is equivalent to if U, V are linearly dependent, then Okay? You agree with this? And this is like a lot easier. I mean, this is sort of a lot easier to show, right? So if so let's prove this part. So if U and V are linearly dependent, if two vectors are linearly dependent, what does that mean? You all agree with that? Yeah. So so we can write U as C times V, for example. So this is the linear dependence of this set. So and then so UV W as a set is the same as CVVW. Is this one linearly dependent or independent? Yeah, because so you can see right away that CV is C times V. So this set is dependent. Mm-hmm.
How did you get that statement, U equals C?
So these two, so when are two vectors linearly dependent?
Oh, and one can be said.
Yeah, I mean, so like you can use like the first part, right? So we can, so if I exist such that one of the vectors can be written as a combination of others, so like one can be written as a combination of the other, meaning one will just be a multiple of the other. Okay?
If you were to prove it like in a different way could you say that C1U plus C2V plus C3W equals 0, where all the C's are equal to 0 if it's linearly independent, and then just say that like getting rid of the W wouldn't make any difference because you're multiplying by 0?
It's so if you write a combination, so you are making, so we have, so you know that, so C1, can we do like write this down in the end? It's a slightly trickier to do it the other way. Yeah, so I would prefer to just go on like with the next slide, so like that I don't get like anyone confused. Okay, so let's go to part C. So for part C, we still have U, V, and W linearly independent. And and now the question is the set 3U plus 2V, V, and U plus V plus W. So is this also linearly independent? Okay, so remember, how do we approach this problem? So we know that U, V, and W are linearly independent, and now we have three other vectors which are a combination of the original vectors. So how do we test linear independence?
We have to prove that C times 3U times V plus C2 times V plus C3 times U times V W equals 0. So we can kind of distribute the different vectors and see.
Yes, exactly. Yes, great. Yeah. So we write down a linear combination and we set it to 0. And now the question is, what are the solutions of this equation in terms of C? So what are the solutions? In terms of C1, C2, C3. So we're solving for C1, C2, and C3. And remember, if 0, 0, 0 is the only solution, then they're independent. If there are other solutions, then they're dependent. Okay, so yeah. So we don't have any information about like these combinations, but we know that U, V, and W are linearly independent. So we're gonna rearrange sort of this left-hand side of the equation to write it as something times U plus something times V plus something times W. So if we look at what's standing next to U, so from this expression we have 3 times C1. And then here we just have V, and here we have C3U. So this is going to be 3 times C1 plus C3 is standing next to U. And now what's standing next to V? Who's going to tell me?
2C1 plus C2 plus C3.
And next to W? So C3W equals 0. Okay, and now, so we're doing problem 1 from winter 2015 midterm. Okay, so now we know that U, V, and W are linearly independent, so we know that this coefficient has to be 0, this coefficient has to be 0, and this one has to be 0. So the first one is 3 times C1 plus C3 equals 0, and the second one is 2 times C1 plus C2 plus C3 equals 0, and the third one is C3 equals 0. Okay, so sort of this is number 1, second coefficient, and the third one. So from the third one, we get right away that C3 equals 0. So from 3, we have C3 equaling 0. And now, so, I mean, technically, you can solve this with a system, but here we don't really have to, right? Because, so I have C3 equaling 0, and then I can go back to equation 1, in which only C1 and C3 appear. So from 1, we get that 3 times C1 plus 0 equals 0, which implies that C1 is 0. And then we go to equation 2. So now, so we have C1 and C3 equaling 0. If we take this into equation 2, we get 2 times 0 plus C2 plus 0 equals 0. And from here, it follows that C2 equals 0. Okay, so the only solution is C1 equals C2 equals C3 equals 0. So this new set of vectors, so this new set of vectors is linearly independent. Okay? So the next, so we are still doing winter 2015, the first midterm, but now it's going to be problem number 3. We're going to do problem number 2 later, because some of the students who can only come in 1 hour will want to see that one done. So. Okay, so we have 2 vectors, U and V, in Rn, and suppose the norm of U equals 1, and the norm of V equals 1/2. And the first question asks, are U plus 2V and U minus 2V orthogonal? Okay, so how do we test orthogonality?
Dot product.
Yeah, so when are two vectors orthogonal? Yeah, so U and V are orthogonal if and only if the dot product of U, their dot product is 0. So if the question here is, so are U plus 2V and U minus 2V orthogonal? What we're going to do is we're going to compute their dot product. And we're going to have to use the properties of dot product. So let's try to, we are looking for U, so let us compute U plus 2V times U minus 2V. Okay, so the only information that we have is about the norm of U and V. So can somebody tell me how to get, so here we have dot product. In what way is a norm of a vector related to the dot product? Mm-hmm.
The normal vector squared is the normal vector of U is U dot squared is U dot V.
Yeah. So the norm squared will be a dot product with the vector of a vector with itself. So this is the first thing to remember. Like this is the first one, and this one is the second. Okay, so we have to compute this, and we have information about the norm, so this formula will come in handy. Yeah, and what we want to show that is, so what we're testing is if this dot product is 0 or not. So what can I do with, so it's like, I know what the norm of U is, I know what the norm of V is, I cannot directly sort of access, I don't have coordinates, right, so you can't just plug in the numbers and compute what this is. But we do, know that a dot product has different nice properties, so how can we simplify this expression? Yeah, so we're going to distribute. So if I take a dot, so this is the same as taking a dot product of U with U, so this would be U dot U, minus dot product of U with, plus dot product of U with minus 2V, and then plus a dot product of 2V with U, and minus, or I'm going to just write plus 2V dot product minus 2V. So we're going to be clear how I'm distributing this. Okay, so I know what the dot product of U with itself is. It's the norm squared. This is norm U squared. So here I have U dot product with minus 2V. I can just write this as minus 2 times U dot V. And then I have plus 2 times V dot U. And how about over here?
Minus 4V.
Yeah, so minus 4 times V dot V, which is just the norm of V squared. Okay, so here we have minus 2 times U dot V, and here we have V dot U. So what's the sort of one property that dot product has?
It's like U dot V equals V dot
Yeah,
V.
so this is called commutative, it's commutative. Okay, so commutative. So this U dot V is the same as V dot U, meaning that minus 2 U dot V and 2 V dot U cancel out. So this will just be norm of U squared minus 4 times norm of V squared. And the information that we have, incidentally, is precisely about the norm of these vectors. So what's the norm of U squared? This one. And the other one? Yeah, so 1 minus 4 times 1/4 is 0. So are these two vectors orthogonal? since u plus 2v dot product of u minus 2v equals 0, these two vectors are orthogonal. Okay. And here, I mean, basically they're testing like all the properties of dot products, right? It's like you have to know the relation of the dot product with the norm. You have to know about like characterization of orthogonality with dot products. There's sort of like a lot of little things that you have to know to do this problem. And then part B says, show that u plus v is a unit vector if and only if v dot v is minus 1 over 8. So do you know what if and only if means? Like if you see a statement if and only if, what do you have to do? Yes, you basically have to prove two statements. I mean, a lot of the times the steps you're doing are like sort of you can go either way from one to the other, like reordering like expressions in an equation, adding something to equations. But it's good to be aware that, so we basically, we're not going to do it that way, but still, we have to prove two statements. So one statement is, if u plus v is a unit vector, then the dot product of u and v is minus 1 over 8. Oh, and so this is still, for the entire problem, we assume that the norm of u is 1 and the norm of v is 1/2, just so. So the second statement is, if dot product of u and v is minus 1 over 8, then u plus v is a unit vector. But as said, sort of like a lot of times, all the steps in between that you're doing are actually equivalences, so you don't like necessarily have to write everything out. Okay, so what does it mean for u plus v to be a unit vector?
The square root of u plus v dot u plus v is 1.
Say it again?
The square root of u plus v dot u plus v is 1. Square root of...
Doesn't it just have a magnitude of 1?
Yeah.
Yeah. Exactly. So this is if and only if the magnitude is 1. Okay? But when you have dot products, it's like you don't really want to work with the norm. You want to work with norm squared, right? Because then you know that like norm squared is the scalar, like the dot product of that vector with itself. So in this case, since norm is a positive number always, this is 1 if and only if the norm of u plus v squared is 1. Right? Technically, it's like if you have something squared equals 1, when going back, you could have two solutions, right? It's like plus 1 and minus 1. But the norm can never be negative. So that's why, like, there is an equivalence over here. Okay? Okay, so now we have norm squared in here, and so we have information about dot products, and we're trying to make a statement about dot products. That's why I sort of took the square, because I know that this is going to be sort of a way for me to get to the dot product of u and v. So, yeah, and earlier we said that magnitude squared is what in terms of dot products?
U plus v times u plus v equals 1.
Yeah. So this is just taking into account that magnitude of the vector squared is the dot product of that vector with itself. Okay, so now I have this written in terms of a dot product, and I can distribute again, right? So this is gonna, so what do I get if I distribute this?
U dot U
Mm-hmm.
plus C2 times U dot V plus V.
Yeah, and here, so you can write it out like as we did earlier, and then use like you can say that you use commutativity, but like oftentimes you don't do that, right? Because you know that dot product is commutative. Okay, so but now, what is like U dot U? We said it's the magnitude of U squared, and if you look, the magnitude of U is 1. So this is going to be, so this is in this situation, we can just, so we're going to replace U dot U with 1. And then, so I don't know anything about U dot V, but I do know something about V dot V. What is V dot V? 1/4. So this is plus 1/4, and it has to equal 1. And okay, so this is an equation, and what I'm going to do, so here is the term I'm looking for basically. So I'm just going to, from this equation, so here we have 1 plus something equals 1. I'm just going to subtract 1 on both sides. So this is the same as saying 2U dot V equals minus 1/4. Okay? And then if I divide both sides of the equation by 2, I get this U dot V is minus 1/8. Which is precisely what we wanted. And sort of the point over here was, we were just, so for all of the statements that we made, there were 2 going both ways, right? It's sort of here, I mean, we just used the fact that magnitude squared is a dot product of this with itself, and then it's sort of, if we write this out, these 2 expressions are the same. Okay?
Wait, when you subtracted 1 and 1/4, wouldn't you get negative 3/4?
So here I have a 1, and here I have a 1. So this one cancels with this one.
Yeah.
And then I have 2 U dot V plus 1/4, and then I take the 1/4 to the other side to get minus 1/4.
Yeah.
Okay? Okay. In most of these cases, there's, I mean, like in these problems, it's like you basically do the same thing. I mean, like we did similar things in sections. You just have to like compute everything and then see what comes out. And like everything is going to work out because like we will prepare the problems so that they will work out. Okay. So now let's go to reduced row echelon form. So this
You didn't have to prove the inverse of that, then that went the other way. That if U dot V equals -1/8, that is also U dot V.
So all the statements that went both ways. So it's like you have to make sure that when you write this, that you write it in this way. I mean, if it's true, right? Sometimes you actually have to like prove things differently, right? And all the statements are not equivalent. I mean, it's not always that easy. But in this case, it is. But so I just wanted to point out that whenever you have an if and only if, you're basically proving 2 statements. And if it's easier for you, you can first show it like if from one follows the other, and then in a lot of cases you're going to see if you go back that you could have done it the other way around as well. And then that's the time, like sort of when you can go back, you can just add the arrow on the other side. So this is problem 4. Winter 2015. So here we suppose A is a fixed real number. And consider a matrix A, which is 1, -1, 1, 2, and A 0. So the first part A says, find with reasoning a basis for the column space CA. Okay, so what do we usually do? So, and then part B will say find the basis for the null space. Maybe we can turn it around and do the null space first. So what? So how do we find a basis for the null space?
Reduce row.
Yes. Okay. So we copy the matrix, and the goal is to get a to get this matrix into reduced or echelon form. So in the left top corner, I have 1. So it's like I'm pretty happy with this one. This will be one of my pivots. So I'm going to leave the first row as it is. So this is 1 minus 1a. But then I want to, so you notice if you have a pivot row, what you want is, so there's going to be one, in a pivot row there's always like one entry which is 1, in a pivot column, there's always one entry which is 1, and all the rest of the entries in the column have to be 0.
Is it supposed to be minus A or A? I'm just wondering.
It says over here that it's A.
Okay, which is on the other side.
Oh, I'm sorry. Yeah. Okay. Yeah, just copy. Yeah. Okay. So and then I have to get rid of this element over here. So that I get a column in which there's one entry 1 and the rest are all 0. So what am I going to do?
The 2 minus row.
Yeah, I'm going to subtract the first row from the first row from the second row. So 1 minus 1 is 0. 2 minus minus 1 is going to be 3, and 0 minus A will be minus A. Okay. Okay. So now, so now I move sort of to the next column, and I see that I'm going to have a pivot here as well because this is not a 0 entry. When you have pivots, you want to have a 1, not a 3 in there. So I'm going to divide the second row by 3, and I'm just going to leave the first one as it is. So I get 0, 1, and minus A over 3. So here I have 2 pivots, but as I said earlier, if you want to have, so for a pivot column, you want just one entry 1 and the others 0. So what we're going to do now is get rid of this minus 1 over here. So how do we do that? Yeah, so we're going to add the second row to the first row. So what we get is 1, 0, and what is A minus A over 3? Yeah, if you couldn't compute that, you should get my cookies. And this is 0, 1, minus A over 3. So is this reduced to echelon form of A?
Yes.
Yes. Okay, so how do we find, whenever you have a matrix and the problem says find the null space, find either the null space or the basis for the null space, so first you want to put the matrix into reduced or echelon form. A lot of times you will already be given the reduced or echelon form, and then you can just, you don't have to do this step. But I included one example so that you don't forget about how it's done. So once we have this, what do we do?
Set up your system.
Yeah, but so we said step 1 would be put it into reduced or echelon form, and then step 2 would be find the pivot variables and the free variables. So this is step 1, and then step 2. So which are the pivot variables? Yeah, so x1 and x2. How about, and there is one free variable, which is x3. So what do we do for step 3?
Express the pivot variable in terms of
Yes. For step 3, express pivot variables in terms of 3 variables. And so we have to express them from this system. So this system says that x1 minus 2 over 3a times x3 equals 0. So that's the first equation of the system. And the second equation is x2, oh wait, this is just plus. And the second equation is going to be x2 minus a over 3 x3 equals 0. Okay? So now we express x1 and x2, which are the pivot variables, in terms of x3, which is the only free variable in the system. So x1 is minus 2 over 3a times x3, and x2 is a over 3 times x3. Okay? Okay, so and then sort of for step 4, you just have to write down what the solution is. So the null space contains all the vectors x1, x2, x3 that satisfy that system. So now what you do is you write the vector, but you substitute the pivot variables expressed in terms of free variables. So instead of x1 for this vector, I'm going to write minus 2 over 3a times x3. Okay? And then instead of x2, I'm going to write a over 3 times x3. And instead of x3, well, I'm just going to keep x3 as it is. And so x3 is called a free variable for a reason. That is because you can just pick like any real number to be x3 and you get a solution of the system. Okay, so this is the null space of A. And when you want to find the basis for the null space, you want to write the null space as a span of some vectors. So a span of what is this set?
That vector.
Yeah, which one?
Yeah, the negative 2, 3a, 3, 1.
Yeah, so negative 2 over 3a. So we pull out the x3, and what we end up with is minus 2 over 3a, a over 3, and 1. So this is the span of minus 2 over 3a, a over 3, and 1.
What's your null space?
The null space is the span of this vector. Okay, yeah? And then, so what is the basis? For the null space? Yeah, so basis is just this single vector, minus 2 over 3a, a over 3, and 1. And it's expressed in terms of a, but that's fine. And so what the nullity, let's remember everything. Yes, because so nullity is the dimension of the null space. So, or with other words, it's the number of vectors in a basis. So this is a basis that contains just one vector, so nullity is 1. And over here, I noticed that, so apparently some students, when they wrote a solution, they added that a can also be a real number. And for that, you're going to lose points because they tell you that a is a fixed real number, like in the beginning. So sort of be careful. If they say something is a fixed number, don't make it a parameter. Okay? Okay, so the reason why I wanted to do the null space first is because I mean we would have to do this whole reduced row echelon form anyway. So okay, so then part B says rather part A says find a basis for the column space of A. So how do we find a basis for the column space of A from the reduced row echelon form?
It corresponds to the pivot, and we write the original, like, I don't know, numbers from A in the rows that we have to pivot.
Yeah. So give me one example. I mean, just give me the example that we were talking about. So what do I have to take? So what's it going to be?
1, 1, and -1.
Yes. Yeah. So how do you get from the reduced row echelon form to the basis of the column space? So okay. So one of the true-false statements that appears a lot is the column space of A the same as the column space of the reduced row echelon form? And the answer is no, it's not always true. But then sometimes there is an option of maybe, right? It's like, is it true, false, or maybe? And in this case, the answer would be maybe, because if you have a matrix which is already in reduced row echelon form, like for example the identity matrix, which just has 1 on the diagonal and zeros off the diagonal, that matrix equals like its reduced row echelon form. So of course the column spaces will be the same in that case. Right? But in general, the column space is not the same as the column space of A is not the same as the column space of the reduced row echelon form. And remember in section we said that if you have the elements of the null space give you dependence relations among. So if you have a non-zero vector in the null space, it will give you a dependence relation between the columns. Right? So because the null space of A is the same as the null space of the reduced row echelon form, this linear dependence will be preserved. So with other words, I mean, and you don't have to remember, you're not going to have to give this argument, but that's sort of the reason why vectors that are columns that are linearly independent in the reduced row echelon form will also be linearly independent in the original in the original matrix. Okay? Yeah. So how do you find a basis for the column space from the reduced row echelon form? You find the pivots, and then then you mark the columns in which those pivots are. In this case, we have a pivot in the first column and in the second column, and then you go back to A and you take the first column and the second column. So columns corresponding to pivot columns in the reduced row echelon form, and those vectors will form a basis for the column space of A.
Why do we say for the null space that it's the span of a vector, but for this one we just say the set of these vectors?
Oh, so this is a basis.
Okay.
Column space itself is the span of these vectors.
Okay.
I mean, we said there as well. Null
So when
space
you're saying it's a basis, you write it as a set, and when you're saying it's with equals, you write it as
yeah. So the null space is a vector subspace, and it's usually going to be a span of something, whereas a basis is like a finite set of vectors with which you can span. That's like the null space.
Got it.
Yeah. So the column space is span of 1, 1, and -1, 2. Okay, and then there is part C to this. And part C says find all solutions to AX equals 1, 1, or say why no solution exists. Does anyone have any idea about how to approach this problem?
So if you have a unique solution to X, then you can just add the null space to that, and you'll have like all the solutions.
Well, so there's like a little contradiction there, because if you have a unique solution, that usually means that the null space is trivial. It's just a zero vector. But yeah, no, but what you want to say is if we find one solution, that is the particular solution, then we get all other solutions by adding like the null space, elements from the null space. Okay, so let's say if x0 is a solution to a of x0 equals 1, 1, then, or maybe, so I'm going to write a general statement. So let's just take B, because this is a general statement. So if x0 is a solution to a of x0 equals B, then all solutions are of the form. So we take x0 and then add elements from the null space. Okay? Yeah, so there are really two ways that you can approach this problem. One is that you just write down the augmented matrix and write 1, 1 on the right-hand side, and you do the whole reduced row echelon form again. But there's a smarter way of doing that, which is by guessing what one solution would be. So can anyone guess what one solution would be? So how did you get that?
Because you just know that you need to have the answer be the vector for T1, and when you do dot product, you multiply each column times each of the other ones.
Yeah. But one good way to approach this is first check if this vector on the right hand side is maybe one of the columns, right? And then remember what we did in section. We said, so what do you have to so how do you get the first column? What vector do you have to multiply the matrix with? 1, 0, 0, the first standard basis vector, right? And then to get the second column, you multiply the matrix with the second basis vector, etc. Okay, so over here you see you see that 1, 1 is in fact the first column of A. So let's go through this 1 minus 1 A 1 2 0. I'm going to put it over here. Times 1 0 0. So 1 times 1 is 1 plus 0 plus 0. So we have 1 over here, and then 1 times 1 is 1 plus 0 plus 0. So we get 1 1. But yeah, but sort of the first if you have a question like that, they're probably you don't have to do the whole reduced row. I mean, you can always do the reduced the augmented matrix and just redo solve the whole system, but oftentimes you can sort of guess what the solution would be.
Does that prove that that's the only solution?
We didn't get to that part yet. So we found one solution.
Could you have just taken 1, 1 because you know that AX 1, 1 is already a solution? You have to.
But no, so X. But so 1, 1 is not a solution, right? It's sort of you have to find something in R3.
Oh, it's 1, 0, 0. Okay.
Yeah, I mean, yeah, it's sort of 1, 1 is the image of that vector, right? You have to find what vector it comes from, basically. Yeah, and if it's one of the columns, you just have to so if that V is one of the columns, you just that particular solution will be one of the standard basis vectors. Okay, so 1, 0, 0 is one solution. So how do we get all other solutions? I wrote it down. Yeah, we have to add elements from the null space, and over here I wrote down what the null space is. So this is one solution, and we know to get all solutions, we just add elements from the null space. So the solution to A of x equals 1, 1 is, so this is the particular solution. And then we add elements from the null space, and we know, so the null space is a span of this vector, so this is going to be plus t times minus 2 over 3a, a over 3, and 1. And t is any real number.
How do you know that you should add the null space?
So that's something we know from the book. It's the statement I wrote over there. Yeah. It's like, I mean, you don't have to reprove this. This you can use. Okay?
What would we do if, like, we couldn't figure out that 1, 0, 0?
Then you just, like, write down the augmented matrix for 1, 1, and solve again.
X2 and X3.
Yeah. And you're going to get the same thing.
Okay.
Yeah, you can do that for practice.
So in terms of thinking intuitively about why we should add into the space there, that's the solution of all things that we.
So these are all the solutions to A.
Okay. And then, yeah, done.
Well, but how, I mean, so, like, if you think about it, right, like, if you take any element, so A of, 1, 0, 0, plus t times minus 2 over 3a over 3 and 1. So now you know that every matrix defines a linear map, right? So basically what you have over here is, like, we're going to use some linearity properties, right? So this is a sum of two, like A of a sum. So what will this linear map do with the sum? So this is the same as A of 1, 0, 0 plus A of t times this vector. So this is the additivity property, right? And then this is 1, 1, and all of this goes to 0. So basically, it's sort of, you can show, like, from this that if there is another solution that sort of, like, the difference from that solution to this one has to lie in the null space. That's how you show it. And it's basically using, like this linearity property of the matrix. And so this goes to 0 because this is in the null space. Okay? Yeah, you can try to prove that for practice. I mean, you don't, as I said, sort of on the exam, you can just write this holds and you're going to get full credit. But for practice, you can play around with it. Okay, so now we're going to do more about vector like one problem from vector subspaces. So now we are doing spring 2014 first midterm. And this is problem 6. So a lot of you sort of going through the coursework web page said, what's the point of like a vector space, like subspace? It's like, why are we doing this? And sort of like in math, it often happens, it's like you have some like very specific spaces, and then you see that they have similar properties, right? So it's like, and then instead of like prove like those properties for each space separately, you want to just make a more general definition and prove things for that. So the way, like we did it in this course, you talked about the null space, you talked about the column space, and the null space and the column space have some nice properties. But they're all vector subspaces, right? So if you have this more general definition, you then don't have to make separate statements about properties of null space or column space. You can just say this holds for all vector spaces, and then you know it holds for null space and for column space. Does that make sense? So sort of like sometimes like having a more general definition will sort of save you like reproving the same statement over and over again, because there are sort of very particular properties that you're using, which is sort of this zero, like the zero vector and closed under addition and closed under scalar multiplication.
For this one, if you did the augmented matrix,
Yeah.
could you find a different point? Like would like 1, 1, 0?
You can, so as long as that's the solution, it's fine. Yeah, you can find a different point. Okay. I mean, you can produce a lot of, like, if you add, like, t's, I mean, whatever other t's, you can get a lot of different points.
But the part in T should always be.
Yeah, that's the null space.
2/3, 1/3.
Yeah, I mean, that's the null space.
Yeah.
Yeah. Okay, so, yeah, I'm not sure that motivates you to do more vector spaces, but sort of, like, before we talked about vector spaces, you sort of wrote down properties of null spaces and of column spaces, and you prove statements, like, and a lot of them, like, would just follow from the fact that they're vector subspaces. So it's like you basically had to learn more statements because you didn't talk about vector spaces from the beginning. Okay, well, but that doesn't really matter. That's sort of just sort of one, I guess, apology for mathematicians for troubling you with vector subspaces. As you've noticed, like in old midterms, definitions are very popular, and problem 6 says, complete the sentence. A set V of vectors in Rn is a linear subspace if. So V is linear vector subspace. So what are the properties?
Zero vectors contained in
So 0 is contained in V.
If B1 and B2 are elements of V, their sum should be V.
Yeah, so this property, so for this we say that V is closed under addition. So if you take any two vectors in V and you add them together, you should get a vector which is also contained in V. Okay, so how about the third property? Yeah, so what do I have to write? So we have V and V and a number C. What has to be contained in V? Yeah, so these are the three properties. And just for knowing the definition, you're going to get some credits already. But it's also going to help you with like the other parts. So part B says, if W, this is the set of all x, y, z, for which 2x equals 3y, and x plus y plus z equals 0, so is this a subspace of R3. Okay, so to prove that something is a subspace, we have to check if all of these three properties are satisfied, of these conditions are satisfied. Okay, so first condition, so is the zero vector contained in that?
Yes.
Yeah, so 2 times 0 equals 3 times 0, and 0 plus 0 plus 0 indeed equals 0. So the first condition is satisfied. And now for the second, condition, so suppose we have a now we have to take any x1, y1, z1, and any x2, y2, and z2, and w. So what we have to do is we have to show that their sum is also contained in W. So you can see, so W contains vectors whose coordinates satisfy these equations. Okay? So x1, y1, z1 is in W. So what conditions do the coordinates of this vector have to satisfy? Oh no, just sort of like now I'm just checking the containment condition. So some vector is in W. Yeah, so it has to satisfy the equations, right? So 2 times x1 has to equal 3 times y1, and x1 plus y1 plus z1 has to equal 0. So this is the condition for x1, y1, z1 being contained in W. And now I can write a similar thing for x2, y2, and z2. So this is in W if and only if 2 times x2 equals 3 times y2, and x2 plus y2 plus z2 equals 0. And so I'm looking, now I have to look at the sum of these. So x1, y1, z1 plus x2, y2, z2. So if you look at the condition for W, it's given in terms of coordinates, right? So it's like here I have a sum of 2 vectors, but I know that if I take a sum, like to get a vector, I just have to take the sum coordinate-wise. Right, so this is just x1 plus x2, y1 plus y2, and z1 plus z2. So I want to write this as a single vector because then I can check the containment condition for W. Okay? Everything clear so far? Okay. Okay, so the first condition is 2 times x1 plus x2 the same as 3 times y1 plus y2. So this is what I have to check. So I'm gonna take like this expression on the left hand side. So this is 2 times x1 plus x2. And so I don't know anything about the sum, but I do know that what 2 times x1 is, and I know what 2 times x2 is. So I'm going to distribute and write this as 2 times x1 plus 2 times x2. Okay?
Just wanted to clarify, so why are you asking that question? Because this is like the ending number.
When is a vector contained in W? If the coordinates satisfy these 2 equations, right? So the question here is W a subspace? So I have to test if this is the same as this, and if like this condition is satisfied for the sum of vectors.
Okay.
Okay? Yeah, so I mean this is sort of now checking the containment condition. So if W is a vector subspace, then this equation has to hold. But I don't know that yet. I have to check if that holds. But what I do know is that 2 times x1 is 3 times y1, and 2 times x2 is 3 times y2. Like that. So it's like what you always do when you check if something is a vector subspace is like write the conditions for like the 2 vectors that you start with. And then from those 2 conditions, you have to prove like that from that it follows that their sum is also contained in that subspace. Okay, so 2 times x1 plus x2 is 2 times x1 plus 2 times x2. And now since since these two vectors are contained in W, we see over here that 2 times x1 is in fact 3 times y1, and 2 times x2 is 3 times y2. So this is 3 times y1 plus 3 times y2. Okay? And now I can just pull out the 3 and write this as 3 times y1 plus y2. And this is precisely sort of the first equation of like the containment condition.
Could plugging in just particular points, but would that work as proof?
Particular points?
Yeah.
No, any 2 points contained in W. If you pick like 1, 0, 1 or something, no.
Okay.
Yeah.
So you have to do it like this.
Yeah, you have to do it like this. I mean, if you're trying to prove that it is a vector subspace, if you are trying to prove that something is not, then it suffices to find just like 2 points for which, for example, the sum is not contained in W, or like one vector which, like a number with which you multiply such that the vector is contained and the multiple is not. Yeah, so for counterexamples, it's enough to find one counterexample. If you're trying to prove something is a vector subspace, you have to take any 2 vectors.
Well, what's an example of something where we would find a counter?
Oh, we did that in class, remember? We can do that. So, I mean, okay, so, for example, I can take wait, this should be pink. Okay, so if you take, for example, in R2, the union of these 2 lines, is this union a subspace?
No, because if you add it,
Yeah.
it would be a diagonal.
Yeah, for example, if you add 1, 0, and if you add 0, 1, you're going to end up with this vector, which is not in the union of these 2 lines.
But the cases in which we would have to find a counterexample would be obvious. Like this one's obvious.
But they're not going to, I don't think they're going to give you anything other than plain. I mean, I might be wrong. It's like because I'm not going to be like selecting the problems for you. But in the previous midterms, most of the time, the counterexamples were in the plane.
But it wouldn't be like this kind of thing where we have to solve some complicated. Like, how do we know if while we're solving that it doesn't work?
I mean, once you have, I mean, if you don't have a good intuition, then you just try to prove it is a vector subspace, and when something fails, that's going to sort of push you in the direction of finding a counterexample. Yeah, that's how it is usually. Sort of try to prove that it works, and then you're going to see it's not going to work out, and so it's like it's probably not true, and then just like I find numbers, like one example that will support like the statement that it's not true.
For that one, could you have just evaluated like 2x plus 1 plus 2x, or 2x1 plus 2x2n equals 3y1 plus 2y2, and then like subtract everything, and then since like 2x1 is 3y1, that's like 0.
I mean, yeah, but the condition over there is given as 2x equals 3y, so I
Okay.
just actually, I mean, just copy down the condition.
Okay.
Yeah. But yeah, if you want to put everything on one side, that's fine. Okay, so this is the first containment, sort of condition for containment, and the other one is, so the sum of these coordinates has to be 0. So the question is if x1 plus y1 plus x2 plus y2 plus x3 plus y3 0. So again, we take the left-hand side, so x1 plus y1 plus x2 plus y2 plus x3 plus y3. Now, we don't know anything about these sums, but what we do know is that x1 plus y1 plus z1 is 0, and we know that x2 plus y2 plus z2 is 0, because these 2 vectors are contained in W. And so now can we rearrange this side so it's going to contain those 2?
Why are the variables set up like that? X1 plus y1? Couldn't we?
Yeah, we have to, so we are checking the containment condition for this vector, which is x1 plus x2, y1 plus y2, z1 plus z2, right? So so for this, instead of this x, I have to write x1 plus x2 in this condition. condition, and instead of y, I have to write y1 plus y2. Instead of z, I have to write z1 plus z2. Because I'm testing it for this vector, which is a sum of two vectors.
Yeah, it's the inside vector is x1 plus y1.
Oh, I'm sorry. Okay, yeah, thank you. So this is x1 plus x2, y1 plus y2, and z1 plus z2. Okay, great. Maybe I should eat more cookies so I can do things like this. Okay, yeah, but what we know is that if we add x1 and y1 and z1, we get a 0. And then what remains is x2 plus y2 plus z2, which is also 0. So this is 0.
Wait, what? How did you? Can you explain that again?
So here we have x1 plus. So this part is okay now, right? So I'm just checking the condition. So I know that x1, y1, z1 is contained in w, which means that the sum of x1, y1, and z1 will be 0. And then because x2, y2, z2 is contained in w, the sum of x2, y2, and z2 is 0. And then you can think, like, I just rearrange them, like, so addition, like ordinary adding, is also commutative, so you can just like flip them around like as much as you want, change the order of adding. And so what you get is 0 plus 0, which is 0. Okay? Yeah, so usually this like closed under addition condition is the hard one to check. Okay, and now we have, so the third condition is, so if we have any number c, and if we have x1, y1, just x, y, z, and w, then c times x, y, z has to also be in w. So, okay, so c is any real number. So when is x, y, z contained in w?
This has been
Yeah. So 2x has to equal 3y, and x plus y plus z has to equal 0. So c times x is the vector cx, cy, cz. So now we have to check that this vector satisfies two containment conditions. So the first one is 2. So is 2 times cx the same as 3 times cy? Is this is this true? Yeah. So we know that 2x equals 3y. So if you multiply both sides of the equation by c, you get that 2 times cx equals 3 times cy. Okay? Yeah?
I'm still confused about that one. Where did you get the z from? Like, I mean, how did you go from x3 plus y3 to z1 plus z2?
when you corrected it, when you changed it.
You mean this is not correct.
Oh, yeah. Oh, and you get that from the...
So this is the containment condition for this vector. This is the same as this condition. Okay? So this containment condition says if you add this, like all the three coordinates together, you have to get 0. The first coordinate is x1 plus x2, the second y1 plus y2, the third one z1 plus z2. So if I add them together, it has to be 0 if this thing is contained in W. Okay? Mm-hmm.
For the line above that, like where you distributed the 2x1 plus 2x2, like how does that prove that 2x equals 3y?
So we are proving that 2 times x1 plus x2 equals 3 times y1 plus y2.
Yeah.
So, what's the problem?
Like, how did you prove that that like matches the condition of 2x equals 3y?
So this is the condition. I
Like,
mean,
you just plugged in like x1 plus x2.
yeah.
Right?
Yeah, and this is 2 times x1 plus 2x2, and now x1, y1, z1 is contained in w, so 2 times x1 has to equal 3 times y. So instead of 2 times x1, I wrote 3 times y1. Instead of 2 times x2, I wrote 3 times y2. And then if you add these together, you can pull out the 3, and get this is 3 times y1 plus y2. Okay? Mm-hmm.
For the bottom row, did you regroup them?
Yes.
So it's for all the 1 subscores and all the 2 subscores together, like x1
Yeah.
plus y1.
Yeah, like the green ones are put together,
Okay, got it.
and then the rest are put together. Okay? Yeah?
No, I'm sorry. I had that up.
Okay. Okay, so now we have, so this is the first containment condition for C, and now we have the second one, which, so we have to check if Cx plus Cy plus Cz equals 0. Is that true?
Yes.
Yeah, so we know that x plus y plus z equals 0, so therefore if we multiply this equation with C, it's going to say that Cx plus, so this is going to imply that Cx plus Cy plus Cz equals 0. But it's sort of, like you can see in all of these cases, it's really important that you use the fact that the vectors that you start with are contained in that space. Otherwise, you're not going to be able to prove it, because it's probably not going to be true.
For the could you say, like, back out to C and be like, if you divide by C on both sides, you end up with x plus y plus z equals 0, and that would
So,
be it.
dividing by C is always tricky, right? Because, like, what if C is 0? Right? There's nothing prevents, that's why I didn't divide by C, because then I would have to say, if C is 0, then this is true, of course, because 0 equals 0. If C is not 0, then I can divide.
Oh, okay.
But I sort of I intentionally like did it this way, because I can always multiply an equation by a number, but it's like with the, when you divide, you have to be careful, because you should not divide by 0.
Oh, okay.
Okay? Yeah, I mean, that's sort of the reason I did it this way. Okay, any questions for this part? And now you're going to see that, I mean, there is sort of a lot easier way of doing this. But, I mean, this is sort of, if you don't have a better idea, do it this way. But, if you, so alternative solution. So remember, sort of early on in the quarter, we talked about null spaces and about how null spaces are related to a solution to a certain system of equations, right? So, like if you look at it over here, this W contains x, y, and z, which solve these two equations, right? So W contains vectors x, y, z, which solve, and now I'm going to put everything on one side, which solve 2x minus 3y equals 0, and x plus y plus z equals 0. And so, can you maybe then, so when we said that the null space of a certain matrix is the set of, like, the solution, basically, to a certain system.
So you can say, like, that is the null space of the matrix, like, 2, 1, or, yeah, 2, 1, 3, 1, 0, 1. And, like, a null space.
So when you have a W given by some equation, like the first thing you want to do is write the coefficient matrix, right? So the coefficient matrix in this case is going to be 2, so this is x sort of y, z, and here we put the coefficients. So 2 minus 3, 0. And over here we have 1, 1, 1. Okay? So basically what this W is the solution to this system. So so W, and so given that coefficient matrix, the null space is the solution, right? So this is the null space of 2, minus 3, 0, 1, 1. I guess this also comes in handy if you have a problem of type, yeah, I don't know, find a matrix such that this will be, you had some of these, like for the previous homework, right? Like you were given some subspaces, and then you had to find a matrix such that that space will be the null space of that matrix. And this is what you did, sort of. Like you find the coefficient matrix. So yeah, so W is given as a set, as a set of solutions to a certain system. So what you can do is you can write down the coefficient matrix, and you know that the null space of that matrix is the solution to the system. But why is this better? Because the fact that a null space is a vector subspace is proved in the book, and you can use that fact. You don't have to reprove it, right? Whereas what we did was we basically reproved that that null spaces are vector subspaces. This is how a general proof would work. Okay? So that's a general statement. Statement which you don't have to prove. So given a matrix A, N of A is a vector subspace. Yeah. So if you think of this, this is where this problem can end. This is going to be like one line versus probably the entire sheet of paper. Okay?
And you do actually have to calculate what the null space is, or?
You have to find the matrix. So the null space, so if you have a coefficient matrix, by definition, like the null space of that coefficient matrix is the set of solutions. It's basically the solution to the system given by that coefficient matrix.
And then do you set those two equations equal to 0?
So when you do the null space, it means that you're setting them to 0.
Right. So how does that prove what we proved with the whole proof thing?
So we proved that W is a null space of a certain coefficient matrix. And you know from class that given any matrix, null space will be a vector subspace.
Oh,
So it's basically using
that it's a subspace. That was the question.
Yeah. The question was show that this is a subspace, and you know and don't have to prove every time that null space and column space of a matrix are vector subspaces. So you can just say this is the null space of blah blah blah, and we know that the null space of a matrix is a vector subspace from the book. Like that's it.
If it wasn't 0, 0, you wouldn't be able to use the null space.
Yeah.
You would have to use it.
Then it probably wouldn't be. Wouldn't be a vector subspace. Yeah.
Wait, what would be a problem in which we would use that?
I mean, this is an alternative solution to showing that W is a vector subspace of R3.
Oh no, but you said earlier that there were problems in the homework that.
So in the homework, there were a couple of examples where you were given a subset or like a subspace, and then you had to find a matrix whose null space that space was.
Wait, so you're given a subspace.
Yeah.
And then you have to find the null space.
Then you have to find the matrix such that that space will be the null space of that matrix.
Well, how do you do that?
You did that in homework.
Oh.
Yeah, we can look at it later, but you did that at homework. I mean, this is how you do it, right? It's like you were given a system of equations, you write down the coefficient matrix for that system, and then you know that sort of the solution of that system will be the null space of this coefficient matrix. So whenever you have W given by some system of equations, just write down the coefficient matrix, and the solution and that thing will be the null space of that coefficient matrix. Okay? Yes, no?
Okay.
Yeah, I mean, yeah, so it's like we have two equations over here, right? And I mean, just here you just have to remember that the null space is basically the solution to a system of equations, right? The null space of a coefficient matrix is the solution to a system of equations given by that coefficient matrix. Okay? Yeah, so write down the system, find the coefficient matrix, and then you know that the solution is by definition the null space of that. Mm-hmm.
Similarly, if we had a system and we could easily prove that it was the column space, could we use that as a justification that some V is a subspace?
Yeah.
Yeah.
Yeah. Although, I mean, most of the time it's going to be that you show that something is a null space. So, yeah. Yeah, but you can. You never have to prove that column space and null space of a matrix are vector subspaces. You show that in class, and you have that in the book. Okay. So, actually, I don't know what exam this is from. Let's see. But it's important. So, and it's not. So I think it's 2014. Like one of the recent exams, and maybe it's autumn, but I'm not sure. And it's problem 1 on that exam. So it's like if you go one exam, like that, you're probably gonna find it. But the problem says, suppose A is a 3x4 matrix, which has the following reduced row echelon form. So the reduced row echelon form is of A is 1, 2, 0, 3, 0, 0, 1, 2, 0, 0, 0, 0. Okay, so the first part would be find the basis for the null space. So and we've done it today already, but this is really important, so let's just do it again. It's gonna be pretty fast. So how do we do this?
Choose your pivot.
Yeah. So pivots are x1 and x3. So what we want to do is we want to express pivots in terms of 3 variables. So how do we express x1 in terms of 3 variables? Yeah, so x1, so we just look at this is from the first equation, and then the second one says that x3 is what? Negative 2x4. Okay, so the null space of A will be, so technically I have a vector x1, x2, x3, x4, but now instead of x1, I'm going to write minus 2 times x2 minus 3 times x4. x2 is a free variable, so just leave it as it is. x3 is minus 2 times x4, and x4 is also a free variable. So this is then x2 and x4 are both real numbers. Okay, so and how can I write this as a span of 2 vectors? What did we say we do? Yeah, so I'm going to sort of like peel off the x2 part, which is, so what do I get? Like, what do I get standing next to x2? Negative 2, 1, 0. Yeah, negative 2, 1, 0, 0. And next to x4? Negative 3, 0, negative 2, 1. And x2, x4 are real numbers. So what is the basis of the null space? I mean, what is the basis of the null space?
Those 2 columns.
Yeah. So minus 1, minus 2, 1, 0, 0. And here we have minus 3, 0, minus 2, 1 is a basis for n of A. but sort of the reason why I wanted to do this problem is not because of part A, but because of part B. So part B says, consider the column space of this matrix. If the columns of A are so if the columns of A are so this is V1, V2, V3, V4. So this is A. We don't know what V1, V2, V3, V4 are. We just know that there are some vectors in R3. Then it says, circle all the sets of vectors below, which give a basis for the column space of A. In other words, we are asking for which of the following sets the vectors span, the following sets of vectors span the column space and are independent. So, and what you are given is, so V1, V2, and V1, V3, V1, V4, V2, V3, V2, V4, V3, V4, V1, V2, V3, V1, V3, V4, V2, V3, V4, and V1, V2, V3, and V4. So, which are a basis for the column space of A. So that's the question. And this question is different from the ones we've done so far, right? Because so far I told you, given reduced to an echelon form of a matrix, you can always find a basis by looking at the pivots and then looking at the corresponding columns in A. But this is different, right? So here they're asking about all the possible bases that you can find for the column space. So does anyone have a thought about how to do this?
Do you know that it can't be any of the ones with 3 elements because the basis has step 2?
Yeah. So okay. So the first step is here we have 2 pivots, which means that the column space of A will be spanned by 2 elements. So we can eliminate these 3 right away. So these ones are out because the reduced echelon form of A has 2 pivots. So the column space of A is going to be 2-dimensional. Okay? Yeah?
I just wanted to clarify, so for which are a basis for CA, so that's the definition of, in the problem itself, it says which following sets span CA and are independent.
Yeah, that's the definition of a basis of a space. So vectors are a basis of V if they span that space and if they're linearly independent.
Okay.
Yeah, so I didn't stress that part because they basically told you the definition of a base, and I'm gonna assume you already know that. So okay, yeah. So we know. So okay, from the technique we looked at earlier, we know that we can look at the pivot columns, and then go back to the columns of A. So this is good. So the first and the third one are pivot columns. So V1 and V3 will be a basis for sure. Okay? So this is going to be one of them. But how do you get all the others? And basically what we're going to do is, so what are the bases for the column space of the reduced row echelon form? Can somebody tell me that? So if I take, so I'm going to write, oops. Thank you. Yeah, so if I take, this is going to be my column 1, column 2, column 3, and column 4. Okay, so that I don't have to write the vectors out every time. So C1 is just 1, 0, 0, C2 is 2, 0, 0, C3 is 0, 1, 0, and C4 is 3, 2, 0. Okay, so so we know that we're looking for 2 vectors, right? So so C1 and C3 we already know are a basis. How about C1 and C2?
No.
No, because these are linearly dependent. But because the null space, so because these two are linearly dependent, V1 and V2 will also be linearly dependent. And this is sort of because the null spaces are the same. So linear dependence relation going from A to the reduced row echelon form is preserved. Okay? So C1 and C2 are not a basis, meaning that we can cross out V1 and V2. Okay? So we have C1, C2 we checked, C1, C3 we checked. How about C1 and C4?
Yes.
Yes. So C1 and C4 are linearly independent. So if we go back to A, V1 and V4 will also be linearly independent. So this is a possible, this is a basis. Okay.
So we're saying that like the reduced row, the basis for the column space in the reduced row echelon version is like analogous to the original one.
The linear independence relation is preserved.
Okay.
Because the null so the point is that the null space of A is the same as the null space of the reduced row echelon form, and the null space is the one that carries information about linear dependence between columns. Okay? So it's sort of if you have two linearly independent columns in reduced row echelon form, the corresponding one in A will also be independent. Okay?
And so you know that they're independent if in one of the rows it's 0, but then in the other one.
Yeah, that's sort of an easy way to check. Yeah. Okay, so C1 and C4 are also a basis, so we circle those. So and then we go. So now we've sort of exhausted all the C1 options, right? So now we take C2, so this is the second column. So if we take the second column and the third column, will this be a basis? Yeah. So that means that if I take the second column in A and third column in A, this will also be a basis. So this is going to be one candidate. So how about C2 and C4?
No, because it doesn't have any of the pivots.
Doesn't matter. So if you look at so basically the span of C2 and C4 is the same as span of C2 and C3, right? Because you have a 2 over here.
But I thought for it to be in the basis for
So that's
the column space, you have to have at least one of the pivot columns.
So one way of getting a basis is to look at the pivot columns and then we'll go back to the to A, and then the corresponding column, the columns corresponding to pivot columns, will be a basis. But it's not going to be the only basis. You can have many different bases. So what you have to do is you have to check so we know that there are going to be two basis elements for the column space, and over here C2 and C4 span the same space as C2 and C3, right? Because it's going to have something on the first coordinate and something on the second coordinate. And you can, if this is confusing, you can just sort of prove, for practice, at least once. So prove that, so this is C2 and C4 now. So prove that span so C2 is 2, 0, 0, and C4 is 3, 2, 0. So prove that the span of this equals the span of 1, 0, 0, and 0, 1, 0. Okay? Yeah, so just, if you don't believe me, do it for practice. Okay? Yeah, but sort of a good indicator is I have to have something in the first coordinate and in the second coordinate. And sort of this C2 will give me the freedom to move along the first coordinate, and this C4 will give me the freedom to move in the second coordinate. Okay? Okay, so C2 and C4 are also a basis. So we circle V2 and V4. And now, so how about C3 and C4? Yeah, it's sort of a similar situation. Now C4 will give me sort of the freedom to move along like the first coordinate and C2, like C3 to move along the second coordinate. Mm-hmm.
For a question like this, typically ask you to like prove that all of these.
No.
Okay.
No, so
Because I can kind of like see that they are.
yeah, no, so here so here you just have to circle. Just circle. Mm-hmm.
For like the proof question like that, could you just say that like both of them are like planes that pass through zero, or do you have to actually like do like that?
I mean, you can have planes going through zero that are not the same planes, right? That's sort of
So would you have to
intersecting
prove
line.
that they're all like
So the way so this is what we did in section 1, sort of worksheet 1, if you remember. So what you would do is you show that 1, 0, 0 can be written in terms of these two vectors, namely it's 1/2 of this vector, and you show that this vector can be written in terms of these two. So this would be taking 1/2 of this and then subtracting an appropriate factor of this one. Yeah. But basically, you show that this one is contained, like, can be written as a combination of these two, and that this one can be written as a combination of these two.
Okay.
Okay? And vice versa. Yeah, so anyway, this is also, like, we didn't have a chance to do this in class, but it's really important, so, yeah, it's like the way you usually, like, we found the basis for the column space, so it's one way of finding it that always works, and if, like, the problem just says find a basis for the column space, that's how you do it, but sometimes they might, like, want more than that, right? They want all the different bases that you can think of. And that's when it's like important that you're aware that if you have the reduced to echelon form, that sort of this the dependence relation between the columns is the same as the dependence relation between the columns of the original matrix. Okay? Okay, now let's see. We're going to be kicked out in 10 minutes. But I think, so I have time. I'm going to do one more. So, okay, I can actually let you decide. Do you want to do true, false, maybe questions, or do you want to do a plain question, sort of plains in R3?
True, false.
True, false. Okay.
I actually agree with that one for sure.
Okay, so this is
True false transformation.
Oh yeah, true, false, subspace, and transformation. I feel like it's a confusing one.
yeah, well, there are a lot of them. Okay.
True, false.
Okay, and I guess if we don't finish. Yeah, so the problem we would do, like the plain problem that I picked would be. Okay, so the plain problem that I picked was winter 2015 problem 2 midterm 1. So the one that we skipped earlier.
Okay.
Winter 2015 problem 2. Okay, so this is winter 2015 and problem 8 is true and false questions. So part A, a set of 3 vectors and R5 is linearly independent. True or false or maybe?
Maybe.
Yes. Yeah, so we can come up with examples of both, right? It's like, okay.
Do they ask us to substantiate our answer by coming up with examples, or
Decide which and circle the appropriate choice. You do not need to justify your answers.
Love that.
Yeah.
But another midterm that's not. Another midterm you have to agree.
But then it wouldn't have so many statements.
Yeah.
Yeah. So a set of 6 vectors in R5 is linearly independent.
false?
False. Yes. I mean, if you had 6 linearly independent vectors, they would span R6, sort of intuitively. Okay. A subspace V. Oh, so these are the ones you like. Subspace V of R3 that is spanned. Okay. So I'm gonna write this down. So we have V of R. So a subspace of R3 V3 spanned by V1, V2, V3, and V4, which are linearly dependent, satisfies V equals R3.
You said linearly dependent or independent?
So they're always going to be linearly dependent because there are four of them in a three-dimensional space.
Maybe.
Yeah, maybe. So, so these are going to be dependent for sure, right? And then, for example, if you pick these two to be standard basis vectors, they're going to span R3. And, for example, you can take, so if you take E1, E2, E3, and E3, so this will span R3. So this set spans R3 if you take a span of it, and then, but you could also take just E1, 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 E1.
That would be false.
Yeah, and in this case, it would span a one-dimensional space because you would just, like, this would be a span of a single vector. Yeah, so like often when you have these like sets, it's like you, so I guess a lot of students think that, oh, if I have three vectors, they must be linearly independent, but it's like, unless the statement says they're linearly independent, you can just write the same vector every time, right? I mean, there's nothing preventing you from doing that. So, yeah, I mean, I guess sort of it's good to keep in mind, if it doesn't say that they're linearly independent or not, so then, I don't know, like, try to see what happens if you make them all, like, what, like, you just write the same vector many times. That's sort of usually a good source of counterexamples for these, statements.
But, sorry, if it's in the span, if it's spanned by those vectors, should those vectors be linear?
No, it doesn't say. So, like
isn't that's not part of the definition of vectors that span?
No. So a span of vectors is a set of all linear combinations. If you have a basis, then you have linear independence. Okay? Okay, so, and then for D says, given a 3x5 matrix A and 4 vectors, so,
So you can have a span of two linearly dependent or collinear vectors, which would span the subspace.
yeah, so remember, so we had that example in class actually, where so you had span of 2, 1, and 4, 2, and then you had to draw it. I mean, something like that for one of the homeworks, and I said, well, let's draw it, right? And I just sort of do look, and it was, wait, it's like they're dependent. Well, doesn't, you can still draw them, right? But the space is going to be just a single line. So when you have a span, there's nothing saying that the vectors, like, that you take a span of have to be linearly independent. If they are, and they span the whole thing, then it's called a basis. That's sort of the minimal spanning set, if you want. And it's like, you like bases because you don't want to have redundancy, right? And it's like if you just repeat one vector 4 times, you have a lot of redundancy. Okay, so part D says, given A, which is a 3x5 matrix, and 4 vectors W1, W2, W3, W4 in R5, then the set AW1, AW2, AW3, AW4 is linearly dependent. So we actually did this problem in one section, not in the other one because we're out of time, but
True.
so
True.
yes, so it's so a more general statement is true. So more general statement. So if you have a linear map T from Rn to Rm linear, so and if vectors v1 through vk are linearly dependent, then A of v1 through A of vk are linearly dependent. that's a more general statement. It's like, it doesn't have to be a 3 by 5. It's like something. Okay?
What's the statement to begin with?
Oh, I'm sorry, here we have T. This statement? So this statement says, given a 3 by 5 matrix A and 4 vectors W1, W2, W3, W4, the set AW1, AW2, AW3, AW4 is linearly dependent. And this statement is always true. And so this is a more general statement that holds. We did this in one section. So if we have a linear map going from Rn to Rm, and if we have so this was also in one of the old midterms, actually. So like,
But you have to memorize them.
so this is not a definition. This is a statement. Yeah. I mean, it's good to keep it in mind. Yeah. I mean, so we can.
Wait,
we were able to answer one true/false question with it, right? So.
Does the statement tell you that W1 through 4 is linearly, they're linearly dependent?
Yeah, it doesn't say that.
Oh wait. Okay. Yeah. Sorry. Yeah. So okay. I sort of read like what I wanted to read, I guess. So this statement is still true. So we have, so if V1 through Vk are linearly dependent, then T of V1 through T of Vk is linearly dependent. Okay, but this one we have to do differently. So, okay, so we have V1 through V4, and we don't know that they're linearly dependent. But, so these are all vectors in R5. Okay? So, and this is like sort of the linear map aspect of these questions. So, if A is a 3 by 5 matrix, where do A of W1, 2, 3, and 4, what space do they live in? R3. Yeah, so these are all in R3. All of these. So what you have is a set of 4 vectors in R3. And can it happen that this set is linearly independent? It can't. Yeah. So okay, so I'm sorry. I guess I was too fast reading. But this is one of the questions that appeared on the old midterm. So it's like, I don't think it appears over here, but it might as well. Mm-hmm.
If V1 through Vk are linearly independent, then does it mean that TV1 through TVk are also?
No, I mean, look at the projection we were looking at today, right? It's like you had like 1, 0, and 0, 1. They were both projected to the line, right? So, yeah.
How do you know that they're in R3?
Because A is a 3 by 5 matrix.
So I think I would get confused because I would think that they'd be in R1.
Yeah, no, so if it's a 3 by 5 matrix, you have 5 columns, and you take a vector in R5, and so this they actually tell you that W1 through W4 are in R5. And then sort of once you do all the multiplication, you end up with a vector in R3 because you have 3 rows.
How would you apply this?
So you cannot apply it here. I mean, this is the statement from the previous midterm. So they can have you prove this.
Oh, you just have to give it that?
Yeah, I mean, this is one of the statements, like, this is one of the questions from the old, like, from one of the old midterms. Yeah, so yeah.
I
Uh-huh.
forgot why you can say how you can know that they're not linearly independent.
So, can you have 4 linearly independent vectors in R3? Because, I mean, they would span R4, sort of intuitively. If you want to prove it rigorously, write down a system of equations. Yeah. Okay, yeah, I'm sorry, I read the question, like, wrong. I thought that they were dependent. But, yeah. Yes. So, given a matrix A, the column space of A is equal to the column space of the reduced to echelon form. True, false, maybe. Maybe. Yes, this is a tricky one, right? It's not generally true, but it's not. But if you take like matrix to be, for example, the identity matrix, which already equals its reduced to echelon form, then it happens to be true. about this one? Given a matrix A, the null space of A is equal to the null space of the reducible echelon form of A. True. Yeah, so these are the two things you should always remember. But it's very popular. Okay, and then I guess there are two more problems with Frank's nullity theorem. I think we are being kicked off, but if you have more questions like this, like we'll stay outside for a little while.
Are you, what are you doing currently?
Definitely got to work on it.
Yeah.
Another classes?
I recorded the whole thing.
Dude, really? You rock.
So please don't show this to anyone else.
No, I'm putting it on YouTube.
No, you shouldn't.